Hello friends, in this series of lectures so far, we have been considering the high temperature behavior of the materials. So if you could recollect, we began by considering the generalized behavior of the material, how the properties of the material would change at high temperature when compared to the ambient temperature. So our overall treatment of the high temperature behavior began with the definition of the high temperature, and subsequently we discussed how the properties of the material change as you increase the temperature. And after which we considered the response of the material to an imposed mechanical condition at high temperature. So we began with the definition of high temperature, consider the change in the properties of the material at high temperature when compared to the ambient temperature, and from then on we moved to consider the response of a material to an imposed mechanical condition at high temperature. Now this involved two aspects. One, to study the behavior of the material at high temperature in response to an imposed mechanical condition, which was usually a tensile stress, and this we studied in the framework of creep. We wanted to see for an imposed loading condition, as the time proceeds, how the behavior of the material or how the response of the material to the imposed mechanical condition with respect to time varied. And in the previous few lectures, we coupled to that behavior the final aspect of it, which is the failure of the material at high temperature. So this is what we have been looking into in these series of lectures. So in these series of lectures, we considered different modules: the definition of the high temperature, the change in the properties of the material at high temperature, the response to the material to an imposed mechanical condition at high temperature that can be categorized into the behavior of the material and failure of the material at high temperature. Now we intend to move into a new aspect of the material behavior at high temperature. We want to study how the surface of the material behaves at high temperature. More particularly, we want to study both the combination of the influence of the temperature and also the environment on the material. So in this lecture and few more lectures moving forward, we will be considering the role of temperature and also the environment on the surface of the material. And I believe there are possibly 6 more lectures involved. So in addition to considering this, we will be considering the role of the environment, the combined role of the environment and the temperature on the material behavior in few lectures, and to add to it we will be considering the strengthening mechanism, the way we can enhance the behavior of the material at high temperature, and with this we will be winding up the series of lectures. So let us begin by considering why we need to understand the influence or the combined influence of the temperature and the environment on the material. So in this lecture, what we will be focusing on is the combined influence of temperature and the environment on the material. Now if you could recollect, or even without considering the high temperature aspect of a material, whenever you want to talk about or whenever you want to use a material in an application rather, you are largely concerned about the life of the material. So when you have to render an economic consideration for an application or a material usage, your focus is largely on the life of the material. So therefore, one component that largely plays a role when you want to use a material in an application is the factor time. And therefore, even while considering the mechanical behavior of the material at high temperature, we considered largely on creep. We did not focus largely on the high temperature tensile testing, but rather we focused on creep, which is the time dependent behavior of the material. Because when you want to use a material in an application, particularly in a high temperature application, you are interested in the life of the material. And even when we considered within the framework of the mechanical behavior of the material, even when we considered the failure of the material, our ultimate goal was to understand the time taken for the failure of the material. So everywhere the aspect that is common is the time. So we are interested in the life of the material or the lifetime of the material in an application. Now at high temperature, if there is an additional factor that influences the lifetime of the material, we are interested in it. And one such factor is the environment. And therefore, naturally, we are inclined to understand the combination of the high temperature and the environment in influencing the life of the material in a particular application. And that is the reason why we want to study the role of environment at high temperature application. To put it simply, the environment, it influences the life of the material. And that is the reason why we are inclined to study the cumulative effect or the combined effect of the temperature and the environment on the life of a material in a given application. Now, when we talk about the environment as it is doesn't play much of a role. It is the reaction between the environment and the material that influences the life of the material. So, as it is, the environment, it doesn't play, or just because you have a definite environment, if the environment is inert, it doesn't react with the material, then there is not much role that is being played by the environment. The only place where the environment plays a role is when it reacts with the material that is being used at the high temperature. And this reaction is often, it eats away the material. So this reaction between the material that you use at the high temperature and the reaction with the environment, it continues to eat away the material, thereby influencing the life of the material. This eating away aspect is what we refer to as the corrosion. Literally, if you could consider the etymology of this word, this means that the eating away of the material. So we are interested in to understand the life of the material at high temperature. So in addition to the high temperature, environment also influences this life. The way the environment influences this life of the material is by reacting with it and by eventually consuming the material, and this consumption is what we technically refer to as the corrosion. So what we will be studying in these few lectures, or considering very briefly in these few lectures, is the influence of temperature on the corrosion of the material. And even though there are different forms of corrosion, we will be largely focusing on the oxidation aspect of it. So we will be largely considering one form of the corrosion which we refer to as the oxidation. Now, in addition to that of the material in the life or material in the high temperature application, in addition to influencing the life of the material in high temperature application, this corrosion also affects the protection of the material hugely. Because if you consider, just for a simpler sake, if you consider the production of steel, when you produce steel, when you form some sort of an ingot out of it, and this ingot you want to transform this ingot into a desired shape, you will heat it, you will forge it. Ultimately, the processing technique involved in any production of a metal is it involves the increasing the temperature of the metal that we are working on. Largely, whenever you want to work on a material or on a metal, specifically metal, using the metal as a heuristic term here, the metal also can be, by metal I also mean the alloys as well. So when you want to process a metal or an alloy, largely high temperature or increase in the temperature is involved. So when you increase the temperature of this metal, there is a significant amount of scales that are being, or oxidation layers that are being formed during the processing techniques. So these have been observed on the industrial level. So in addition to a material being used in a high temperature application, during the processing of a metal or an alloy, you have a significant loss because of this corrosion or more specifically the oxidation. Now there is a study that was being done in 2007, and this study was largely confined to the steel plants in UK, and they observed that the oxidation, it consumed or close to 1 to 2% of the overall steel that was manufactured in UK. So if you consider the steel that was manufactured in the year 2000 in all the steel plants in UK, 1 to 2% of the steel that was produced was lost because due to this oxidation. Now, in addition to the loss that you suffer while producing the steel because of this oxidation, you have to get rid of it and you have to reprocess the material. So therefore, the loss is significant, and this loss because of this oxidation gets more pronounced when you have a high temperature treatment of the material. So the need for understanding the high temperature oxidation is not confined to the application of the material in a high temperature application, but it is also related to the different processing techniques you employ while you treat a metal or an alloy. So when you treat a metal or an alloy, when you are able to understand the oxidation rate and the oxidation mechanism, and you are able to understand a mechanism or a way in which you can get rid of it or you can reduce it, you also render a useful purpose to the processing aspect of the material. So the reason we need to understand, the reason to for us to focus on the high temperature oxidation, it extends beyond the high temperature application and also to the realm of the processing techniques of metals and alloys. So like I said, the 2000 study, they found out that 1 to 2% of their steel production was consumed by oxidation. So it could be, you could rather think that 1 to 2% is rather trivial, but if you convert it into the metric ton, it is close to 26 to 30 metric tons of steel. So you lose the 30 metric tons of steel just by this oxidation. So that is the reason, or that is the weight of oxidation in the realm of processing techniques, and that is one additional factor or additional reason why we need to understand when we consider the high temperature behavior of the material. We also need to consider high temperature corrosion, particularly high temperature oxidation. Now the reason why we need to consider the high temperature oxidation is because the oxidation, it occurs when the metal is exposed to the air. So we don't have to have a specific environment for this corrosion to take place. Rather, this form of corrosion, it generally happens when you expose the material to air, and that is the reason why we focus on this particular mode of corrosion. Now, when we began considering the high temperature behavior of the material in this series of lectures, the first two lectures were largely dedicated to defining what an high temperature is. If you could recollect, we gave several different descriptions for the high temperature, and these descriptions were largely subjective to the metals. There was one particular description that was a generalized one that gave us a range of temperature, but we soon found out that this temperature or this range of temperature that pertained to the high temperature application was not, it did not do justice to a wide range of metals that were being used in the high temperature application. So we moved on to other definitions which were rather subjective to the metals that are being used at the high temperatures. So these definitions were related to the melting point of the different metals that are being, or metals or alloys again heuristically. So metals or alloys that are being used at the high temperature. Now, in addition to this definition, since the oxidation or the aspect of the material behavior that we are studying now concerns with the environment, we need to also have a generalized expression or generalized definition for the high temperature. Again, the definition that we have been considering so far was in relation to the metal that is being used at the high temperature. Now, the aspect or the behavior of the material or the behavior that we are studying does not only concern the metal or the alloy, it also concerns the environment as well. We need to have a definition that combines both the material that is degrading or material that is behaving at in the presence of this environment, and also the environment that is imposing an effect of the material behavior. So a common definition or a definition that is fundamentally accepted or that is generally accepted while considering the high temperature corrosion or high temperature oxidation is something like this. So whenever you have a temperature wherein the water is in the form of the vapor, so this with reference to the environment, we refer to that as the high temperature. So any temperature that is above 1000 degrees Celsius, or rather, 100 degrees Celsius, we refer to as the high temperature with respect to the environment. So again, this definition We introduce this because we are considering a behavior of the material at high temperature in the presence of the environment. And if you want to consider the definition of high temperature with respect to the environment is the temperature above which the water is in the form of vapor. So this is the more generalized definition. This is the generalized definition, and this is the specific one. The reason why I am differentiating this is because in several applications the pressure is beyond the atmospheric pressure, so that in those cases the boiling point of the water will vary. So therefore the generalized definition for the high temperature with respect to the environment is the environment wherein the water is found not in its liquid state but in the vapor state. So those temperature with respect to the environment are referred to as the high temperature. And since in many applications the pressure that is being maintained is above the atmospheric pressure, there might be a significant difference in the boiling point of the water. So the generalized expression involves the state of the water. So in the temperature wherein the water is in the vapor form, that temperature with respect to the environment, or that environment wherein the water is in the vapor form, is the high temperature environment. Now, even though our focus is largely on oxidation, let us begin by considering the different forms of environment or different corrosive environment that a material might be exposed to in a given application. So let us consider the different corrosive environment. So this being or this section of the lecture being rather the introduction to the high temperature corrosion, we will be proceeding rather in a slow pace. So let us just consider for a few minutes what are the different corrosive environment that one could observe in different high temperature application. So one of the common environment is the air, particularly the oxygen. So but considering, or if you consider a heating element, one that we use domestically, this heating element, once it has served its purpose, and once you let it cool in the air, and air it consists considerable amount of oxygen. So therefore one high temperature application wherein the material is exposed to the air or the oxygen through the air or in the air is the heating element, or the heating element that we use domestically, be it heating coil or whatnot. So one of the corrosive environment, or the most important one when you consider the domestic application, is the air that surrounds us, and particularly the high percentage of oxygen in that air. The other environment that is corrosive or to which the high temperature materials are exposed to is the vapors. Supposing you have, if you look into the different power plants, you have boilers and you have pipes that carry the steam through from the boilers, and these pipes, they are made up of high temperature materials, and these pipes that are the steams that they carry, they form or they render a corrosive environment to the materials that form the pipe. So these are another form of the corrosive environment to which the high temperature materials are exposed to. So the vapors, they largely form, or they form the part of the power plants. Particularly in the power plants, we have boilers, we have pipes that carry the steam, and these vapors in those applications, they act as the corrosive medium, and the materials that are used in the high temperature applications within the realm of the power plants, they get corroded because of their exposure to the vapors. And whenever you are employing a material to these power plants, then we need to consider the influence of vapors on the life of the material. There are other corrosive environments like carbon and oxides that are formed from carbon. Now again, there are several examples wherein you could find wherein you have the oxides of carbon and carbon directly, which are present in the form, or which are mixed in the environment, that influence the life of the material, particularly in the high temperature applications. So one example is the nuclear power plant, wherein recently the carbon based materials are being used as a coolant, and these carbon, they react with the environment and they form the different oxides of carbon. So there are different oxides of carbon, and these carbon and their oxides, it renders a corrosive environment, or it offers a corrosive environment to the material that is used for the structural purposes in the nuclear power plants. So finally, there are several other corrosive environments that are specific to a given elements, like there are sulfur based corrosive environment, nitrogen, hydrogen. There are several in gas based or specific gas based or an element based corrosive environment, and the applications, or rather the reach, or if you consider the amount of high temperature materials that are exposed to these specific environments, are rather minimal. But when compared to all these others, the ones that we have considered so far, when compared to these, there is one other corrosive environment that is largely observed in the high temperature application. So that is the combustion product, or the products of combustion. So the products of combustion may be in the forms of the oxides of carbon, they may be in the forms of oxygens at high temperature. So these combustion products, they form the corrosive environment in the applications wherein you have turbines. So whenever you have turbines, you have you render an internal combustion in them, you render some sort of a combustion in them. You have a compression chamber, and you have a combustion chamber, and you have the actual turbine wings that are being that form the part of the turbines. So in those applications, you have, or the corrosive environment is rather different from all the ones that we have seen so far, and they also form a rather render a rather significant influence on the life of the materials. So these are the different corrosive environment from the point of view of the applications. So when you consider the high temperature application of the materials, and when you want to consider the environment, the corrosive environment to which the material will be exposed to, so these are the predominant corrosive environment to which the material will be exposed to during its role in the high temperature applications. So one is the air, as we have seen, it's rather common in the heating elements or domestic heating elements, and vapor, it is a part, or this corrosive environment is observed when you have boilers and pipe carrying the steams to the turbine. And the other form of the corrosive environment that is observed in the application is the carbon and the oxides of carbon. So one example is the nuclear power plants, wherein you have carbon based coolants. And finally, when you consider the turbines and the high temperature application of material that are being used in the turbines, these materials are exposed to combustion products that render a corrosive environment to, or they render or a corrosive influence to the materials that are being used in these turbines. Now let us get back to focusing on the oxidation, or one of the corrosive environment here, that is the air, or more generally the oxidation. So let us begin with the consideration of the effect of air, or particularly the predominant presence of oxygen in the environment on the high temperature behavior of the material. Now what we essentially have during the oxidation of the material, or specifically again a metal, is a chemical reaction. So this chemical reaction that translates into the oxidation, which we from our naked eye observe as the corrosion, this chemical reaction in its generalized form can be expressed something like this. So a generalized expression for the oxidation can be expressed in this manner. So it should be y here, and these x and y are the stoichiometric terms. So this is a generalized expression for the chemical reaction that ultimately translates to the oxidation of the metal at any temperature. So this is just a generalized expression for the oxidation of a metal, that is M, and you have the oxygen being represented by O2, and the X and Y are the stoichiometric terms that you can observe here. Now, instead of considering this generalized term, for the sake of our discussion, we will restrict or we will have a rather representative expression for the oxidation, which has also been observed in different metals. So it is not something that we use for just the theoretical purpose. We will consider a rather representative expression instead of the generalized one. And this representative is not purely theoretical, it is also observed in several metals. So this representative expression will assume that X and Y is equal to 1. The stoichiometric terms are equal to 1. So that means in case of for the consideration that we are going to render for the course of this study, the expression for the oxidation is of this form: M plus half of O2 is equal to MO. So even though this is the generalized expression for the oxidation, we will be confining ourselves to this expression, and again this is not a purely theoretical one. So this form of oxidation has been observed in several metals, and that's for, and since this enables us to get rid of the stoichiometric terms, we will confine ourselves to this particular form of oxidation. So let us now consider the mechanism of the oxidation. Again, we are considering the oxidation in pure metal. We are not talking about any alloys here, we are just considering the oxidation in pure metal. Now, this particular oxidation, we are talking it in the terms of, or in the context of, the influence of the environment on the high temperature behavior of the material. So what you essentially have is, you have your metal, and that is being exposed to a specific environment, and this environment for our consideration, for our present discussion, is the air, and this air which comprises of the predominant amount of oxygen. Now once this particular metal is exposed to the air, you have a reaction with the oxygen that is of this form here, and it forms an initial layer of oxide. So you have an MO, that is a metal oxide, that is formed by the reaction of the metal to the oxygen. So this is sometimes called as the redox reaction. What you have is the metal that loses its electron, and the oxygen gains these electrons and leads to the formation of this metal oxide. Now what we essentially have after the initial stage, what we essentially have is three different materials. So one is the actual metal, and the metal oxide that is being formed, that is formed after its exposure to the oxygen rich environment, and here we have the oxygen or the air. So this is the oxygen rich environment. So we have three different so to speak one environment and two different materials. So you have your metal, you have your metal oxide, and you have your oxygen rich environment. In addition to that, you have two interfaces. The one interface between the metal and the metal oxide. So this interface is between the metal and the metal oxide, and this interface is between the metal oxide and the oxygen rich environment. So what we need to consider while considering the mechanism of oxidation, we need to initially understand that once you expose your material to an oxygen rich environment, there is an initial scale or the layer of metal oxide that is being formed. So once this metal oxide is being formed, then you have now three different systems. The one system is the actual pure metal, the other system is the metal oxide that has been formed with the reaction to the oxygen, and the third system is the oxygen rich environment. Now this metal oxide is rather a thin layer. We refer to it as the scale, so it is a rather a thin layer, but we are interested in the corrosion or the consumption of the metal. So that means we want to see how this metal oxide grows. So when we are talking about in the context of oxidation, the thickness of this metal oxide is rather minimal, but when you want to talk about oxidation as a whole, we want to see how the metal is being consumed, the actual metal, how it is being increasingly consumed. So that is what our main focus is. So when we are talking about the mechanism of oxidation, we are not restricting ourselves to the formation of the scale. The formation of the scale is just a chemical reaction. But when we want to talk about the oxidation as a form of the corrosion, we want to see the consumption of this metal here. And therefore, we want to see how this metal is being consumed when we consider the oxidation mechanism. This is something that you need to understand. So the oxidation mechanism, it is not restricted to the formation of the scale here or this layer of MO, but it is associated with the consumption of the metal, because MO, the formation of MO, is nothing but the formation, or it's nothing but a chemical reaction. Now there are different ways this metal can be consumed, meaning the oxidation can proceed in different manner. So one way is, so as we have already seen, that this metal here, it loses the electrons and it forms an ion of this fashion, and it also produces 2 electrons. Now this ion can propagate through the metal oxide and reach the interface between the metal oxide and the oxygen. So this ion, M2 plus ion, it can propagate through the metal oxide and reach the interface between the metal oxide and the oxygen, and here the reaction can takes place. So this is one way the oxidation mechanism can proceed, that is the metal oxide. So this is dependent on the propagation of the metal ion across the metal oxide, and here you would have your, so along with this, these 2 electrons will also propagate, and here the oxygen will gain these 2 electrons, or rather this is the O2 minus will be produced by the oxygen gaining these 2 electrons, and these 2, M2 plus and the M2 minus, will ultimately lead to the formation of 2MO. So there is one mechanism where the metal, after transforming into an ion, a positive ion, it propagates across the metal oxide layer and reaches the interface between the metal oxide and the oxygen and transforms into MO. So thereby the MO gets increasingly deposited in this region. So this is one mechanism, the mechanism which is governed by the propagation of MO through, or rather the propagation of metal ion M2 plus through the MO. So there is also another mechanism. So in this mechanism, what we essentially have is the accumulation or the MO being formed in this region here. So the MO will be built on the existing interface between MO and O2. If you could recollect, once you have 3 systems, you have 2 interfaces. So this interface is between metal and metal oxide, and this interface is between the metal oxide and the environment. And in this first mechanism, wherein the metal ion is this M2 plus, this ion is propagating through the MO in this method, or in this mechanism, wherein this is characterized by the propagation of M2 plus through this MO, you have the growth of the oxidation is by building or by the movement of this particular interface. This interface shifts and this MO layer grows. Now there is another mechanism for the oxidation. So in this mechanism, it is rather fairly now easy for you to postulate what could be the other mechanism. So in this mechanism, what happens is, instead of M2 plus, the metal ion propagating through the MO, you have the oxygen 2 minus propagating through the metal oxide layer. So what you essentially have, you have the formation of M2 plus and, or rather 2E minus. This 2E minus propagates across the MO, and since the propagation of 2E minus is rather faster, it is not it will not be deemed as the propagation that characterizes the mechanism. But once these 2 minus reaches the surface or the interface between MO and O2, the O2, it collects these 2 minus, forms these O2 minus and propagates across. So this forms O2 minus, and this O2 minus propagates to O2 minus rather, and this O2 minus propagates across the MO, and then it reaches the metal oxide interface, and there it reacts with the M2 plus. and ultimately leading to the formation of the metal oxide. So there are two mechanisms. In one mechanism, what you have is the propagation of the metal ion across the metal oxide to reach the metal oxide oxygen interface, and there it reacts with the oxygen 2 minus, which is formed because you have a 2 electron that is propagating along with the metal ion. So the metal ion and the 2 electron propagates across the metal oxide, and the metal ion and the electrons, and this electron it reacts with the oxygen and it forms the negatively charged oxygen ion. These two react and they form the MO, or the metal oxide, in the interface between MO and O2. So in this interface you have the formation of the metal oxide. However, there is a second mechanism. So in this mechanism you have first the propagation of the electrons to the MO and O2 interface, and there it changes the neutral oxygen to negatively charged oxygen ion, and this negatively charged oxygen ion it propagates across the MO, and then it reacts with the metal ion, ultimately leading to the formation of metal oxide. Now what happens is the newly formed metal oxide will grow in this region here. So we distinguish it. So in this mechanism wherein you have the propagation of the negatively charged oxygen, the reaction with the metal and the propagation of the interface will be in this direction. And here we saw when the metal ion propagates across the MO, the increase in the metal oxide layer will be in this direction. So what you have is the internal interface that is growing. Rather, we have the increase in the width of the metal oxide by the migration or the internal migration of this particular interface here in case of mechanism 2. In case of mechanism 1, it is the movement of this interface that increases the width of the metal oxide. So you have two distinct mechanisms. In one mechanism, the M2 plus it moves across the MO and it leads, or rather the existing metal oxide, and this M2 moves across the existing metal oxide and reacts with the oxygen ion, because this oxygen ion is formed by the simultaneous propagation of M2 plus and 2E minus. So because of the simultaneous propagation you already have the reactant O2 minus, and these two leads to the formation of the newly formed metal oxide. The newly formed metal oxide it builds in the MO and O2 interface. So the building up of the newly formed metal oxide is in the MO and O2 interface. In case of the second mechanism, you have O2 minus that is propagating across the MO. So it is propagating across the MO to react with M2 plus, and ultimately leading to the formation of MO. Now here, so this MO is the bar, it's the initial one. So as opposed to the mechanism 1, you have O2 minus propagating across the MO. Now the metal oxide, that is MO, that is being formed due to this mechanism, it is formed in the MO and the metal oxide interface. So these are the characteristic difference between the two different mechanisms, and both are governed by the propagation of different ions. The one is governed by the positive metal ion, the other is governed by the negative metal ion. Now in this case, when you have the accumulation of newly formed layer on MO and O2 interface, that is you have two interfaces. So this one we can refer to as the internal interface, and this one we can refer to as the external interface. And the oxidation in the mechanism 1 is seen as the growth of the external interface, and the mechanism of the second mechanism, the oxidation can be seen as the growth of the internal interface. So you have two different interfaces. this interface here M bar MO, and this interface here MO bar O2, that is the interface between metal and metal oxide, this interface between metal oxide and oxygen. So this interface can be referred to as the external one, and this interface can be referred to as the internal one. In case of mechanism 2, the growth of the oxidation or increase in the oxidation is by the movement of the internal interface, whereas in case of mechanism 1, it is by the movement of the external interface. So growth happens in this manner in case of mechanism 1, the growth happens in this manner in case of mechanism 2. Now the reason we want to distinguish these two mechanisms is because when the growth happens in this because of or through the mechanism 1, it is possible that the increase in the oxidation layer, because of its nature, it can be removed. The newly added oxidation layer, because it is exposed to the rather corrosive environment, it can be removed. Thereby, the thickness might remain same, thereby allowing a significant amount of M2 plus ions to pass through. What we essentially mean by that is, when you have two different mechanisms, and in these two different mechanisms, in one mechanism the growth is in the external direction, the new layers that are being formed can be easily removed. So the thickness of the material, even though, or the thickness of the metal oxide, even though it might appear to be the same, the metal gets eventually, or the consumption of the metals does not remain the same, or it doesn't mean that it is stopped. Even though the thickness of the metal oxide, it remains the same, it doesn't mean that the consumption of the metal is stopped. This is because when you have the formation of new layers on the external interface, this external interface, because of the nature of the new layers that are being formed, it is possible in certain environment it gets removed. So therefore, even though the metal oxide size might remain the same, the consumption of the metal continues. So this is one aspect that you need to understand when you are differentiating the two different mechanisms of the oxidation. In the first mechanism, which is characterized by the movement or the propagation of the metal ion and the building up of the oxide layers in the external interface, it is possible that the newly formed layers are removed. Therefore, the MO is more or less remains independent or remains constant. It appears as though the metal consumption is being stopped. However, that might not be the case. So this is one aspect, or one interesting aspect of the mechanism 1 when compared to mechanism 2. Because in case of mechanism 2, since it is the internal interface that is propagating in order to increase the metal oxide, and the oxide that you already have are more or less the stable one. When compared to here, the oxides that form, they are usually a newly formed one and relatively unstable. In this case, the oxides that you have, the external interface is more or less stable. So therefore, that ambiguity will not be observed in the mechanism 1. However, you have to render such consideration when you have an oxidation that is occurring through the mechanism 1. In case of mechanism 1, it is possible that the newly formed metal oxide might be removed and the thickness might appear to be constant, indicating that the consumption of material or the consumption of metal has stopped. However, this should not be, or this is not usually the case. The constant nature of the MO is because the newly formed metal oxides, because they are exposed to the environment, and due to the newly formed nature, they are usually easily removed. So this is something that you need to consider when you are comparing the two different mechanisms of oxidation. Now, in this consideration, or the formation of the metal oxide, we can treat the metal oxide. So this mechanism here, this is not something that is specific to a temperature. So this is just a generalized mechanism of how the oxides are formed, or how the oxidation takes place in a pure metals. So these are two different mechanisms, or this is not specific, or this does not render or add to our understanding of the high temperature behavior of the material. So this is just a generalized mechanism. This can happen at any temperature. However, one aspect that we can be sure about is the migration of the ions, be it the metal ion or the oxygen ion. This migration will be dependent on the temperature. So therefore, even when you are considering the mechanism alone, it is possible for us to understand that the temperature will influence the oxidation. So this understanding can be gained by just seeing the overall mechanism of the oxidation. The overall mechanism of the oxidation involves the migration of the ions. It can be the metal ion or it can be the oxidation oxygen ion. Since the oxidation as a whole is governed by the migration of these positive or negative ions, and at high temperature the rate of this migration would vary. So that means just by considering the oxidation alone, we can say the temperature renders an influence to the oxidation mechanism or to the rate of the oxidation mechanism. So this is something without going into any specific aspects of how a temperature influences the oxidation. Just by considering the mechanism alone, we can say, since the mechanism involves the migration or the propagation of two different of the metal ion or the oxygen ion, we can just say that since at high temperature the propagation might vary, so correspondingly the rate of oxidation might also vary. The other aspect that we can also understand or how an high temperature would influence the oxidation can also again be understood by considering the mechanism of oxidation. Like we have seen that it is possible the newly formed layer, particularly in case of mechanism 1, the newly formed layer can be easily removed as they are formed in the external interface. So this removal is also a form of the reaction, or it's a form of a deterioration, which again depends on the diffusion or the migration of MO. So therefore this migration or this deterioration will also be influenced by the temperature. So what we can also say is that both, so if we assume the formation of the extra layer of metal oxide in the external interface, and we are talking about this extra layer of metal oxide in the internal interface, the deterioration of it, and this deterioration is nothing but the breakaway of this newly formed metal oxide. And when you have a breakaway, when you have a migration that leads to the deterioration of the newly formed metal oxide, when you have some sort of a mobility, some sort of a movement, it is influenced by the temperature. So therefore, in addition to influencing the kinetics of the oxidation by influencing the migration of the ions, the temperature also governs the oxidation mechanism through the stability of the newly formed oxides. So the temperature, it governs the oxidation in two ways. One is by controlling the kinetics of the propagation of these ions that principally govern the formation of metal oxide. The other is by causing the deterioration of the newly formed metal oxide, particularly in case of mechanism 1, wherein the metal oxide are formed in the external interface. So by causing the deterioration, temperature can also influence the overall oxidation mechanism. So the influence of the temperature, just by considering the oxidation mechanism alone, can be expressed in terms of the rate and stability. So the influence, rather use black. So the influence of temperature in oxidation, that is the formation of MO, metal oxide, can be discussed in two ways. One is in the form of its rate. So how the temperature influences the rate of the oxidation and how the temperature influences the stability of the oxides that are being formed. So these are the two aspects which are ways in which the temperature influences the oxidation, and this can be understood at this directly by considering the oxidation mechanism alone. So we will in the next lecture see how the temperature influences the stability of the oxide and also how the temperature influences the rate of the oxidation process. So this influence of the temperature, which we, without getting into any specifics, which we gained just by considering the oxidation mechanism, we will see in the next lecture. So we will continue with this discussion on the influence of temperature on the oxidation with respect to rate and stability in the next lecture. Goodbye.